B part 4, lecture 23rd, important consideration about conservation of angular momentum. You see, this lecture is quite important for you to understand. You see, when you have the rotation is invariant, you see, this leads to you using the Northwest theorem, then this leads to the conservation of angular momentum, you see. But before that, you see a very, very important concept that I will present in this lecture, which I'm sure in the literature is a little confused. You see, that's for you to grasp this concept, which are very important. So, from vector calculus or classical mechanics or electromagnetism, you see, I did present many terms, okay, till 6 over here, you see, just to lead to the angular momentum, okay, that the conserved angular momentum. So let's start from definition and coordinate system. We'll work attention now on the space R3, Euclidean space, but we consider the motion in the xy plane. You see why. That's a very simple model. So let first the position vector, you see, is expressed in terms of the Cartesian coordinates, which varies with the time, you see. So that's the velocity v, you see, the derivative of r with respect to the time. This is x dot and y dot here, see. And now the force F is mass times the acceleration. This is a Newton's second law. Then this is the angular momentum is defined by L. Don't confuse this L over here with the Lagrangian, okay? That has nothing to do with Lagrangian. So this is a cross product between the position vector and P. P is momentum. So in this case, P is momentum, is mv. M is the mass of the particle. And here is the torque, which the definition is the cross product between the position vector and a vector F. You see, that's F is m times acceleration. See, that's r cross r double dot. Now, angular momentum, the definition, okay, is this. This is a cross product. I just use Cartesian coordinates. So this is determinant, ijk, xyz, mx dot, my dot, and mz dot. So I want only the z component. Then I cross here on k. This determinant here, the minor, will be this product here minus this product over here, which is written just over here. You see, this is the z direction. Okay, that's because the motion is on the plane. You see, that's why we have only x and y. And the torque, by definition, is the cross product r cross f. You see, remember, f is m r double dot, the acceleration. The same, I use determinant here. So this x, y, and z are the Cartesian coordinates of this vector here, the position vector. Then I want only in the z direction, so this will be the determinant here. You see, I multiply, you see, x, y double dot minus y, x double dot, or here. This implies, this is my component of the torque, the vector, torque is m times this minor determinant over there. So this is number 3. Now let's jump to number 4. Time derivative of the angular momentum. You see, this is dl of the zt. Attention now, this over here is a product. This is a product. So I expanded this here in two terms and this in two terms. It's just right over here. That's from calculus, okay? So then I can cancel x dot y and this x dot y. I cancel. This leads to just in this space x y double dot minus y x double dot, which is written over here. So this is the z component of the torque. Now, attention. Observe if this component is zero, you see the result of this derivative will be zero, which implies that Lz will be constant. So the angular momentum is constant, will be conserved if the torque is zero. See, that's a very important consideration. Now, then I wrote over here, see, the angular momentum Lz is conserved, that is, R cross F is equal to 0, which implies that the force must be a central force. You see, what is central force? Just as, for instance, you just have, let's put here, the F, let's put here F, or plus in the one direction or the other direction is F, or minus F. You see, and then it's parallel over here. You just have the vector I'm sorry. There's unit vector here, right here. You see? There's unit vector. So the cross product, when they are parallel, okay, this is 0. So if it's very clear, in this case, tau is equal to 0, the angular momentum Lz is conserved. There is R cross F is equal to 0. Attention now, the force must be central. You see, the force, this is, for instance, this is Rx, axis. This is, you see, the force, okay, in the same direction of this vector. If this happens, it's easy. You see, you just substitute here, okay, this in this case, okay, a function times R. You see that, okay, ahead. So the force must be central. It must point along the radius vector toward or away from the fixed point. See, that's exactly what I wrote over here. So in this case over here, okay, this implies that the torque will be 0. And then the angular momentum will be conserved. That's important here. So now, say 5, conservation force. Attention. Why you call conservation force? This is represented by a gradient of a scalar. Attention now, a tensor theory, a gradient increase the order of the tensor by 1. So a scalar is order 0, 0th order. So the gradient is a vector. So F is minus grade of phi. In this case, the work, I can obtain the work for 1 to 2. You see, this is minus. You see the gradient scalar dr. But grade of phi scalar dr is the exact differential of phi. Integral of exact differential, you just doesn't depend on the path. You see, depends only on the initial and final values. This is what happened here. So this is phi1 minus phi2. You see, because this is a minus here, okay? If you remain the minus here, it will be phi2 minus phi1. Then you multiply by minus, is phi1 minus phi2. That's why we say that's conserved, because it does not depend on the path, Okay, many situations in physics, okay, they we say they can be represented by a gradient of a scalar. Okay, why? Because they don't depend on the path between 2 points. Now, then when it's conservative, I can substitute here. You see, look, R cross F. This is different from 0 in general, you see, because the component of the tau, the torque, is also different from 0. And then the derivative of Lz respect to dt is also 0. You just look at, I wrote here somewhere, you see. Then I wrote the result. Okay, look at here and look at here, you see. Look at here, you see. If this is different from 0, L is not conserved, you see. So it's clear from here, you see. So in this case, R cross F is different from 0. The component tau is different from 0, which leads to the derivative of Lz dt is different from 0. And then L is not conserved. Don't be confused, okay? When you have in this case a conserved force, okay, does not imply necessarily that the angular momentum will be conserved. You see, conserved force does not imply necessarily that the angular momentum will be constant. Okay, so that's it. Now, one example for you to see this. Suppose the scalar, okay, function of the plane is x squared. Let's calculate the gradient. The gradient is minus 2xi. Gradient is a vector. This f is conservative, okay, because f is represented by, in this case, a gradient. See, so it's called